Alright, so let's finish the ocean thermal energy conversion system. So what did we say last time? We said there is hot water at the surface and there's cold water at the bottom. And so we can use this hot water as, like at point 1 here, as a source for creating steam. By flashing, you go to 2F and 2G. Liquid that gets sent back to the ocean, and steam 2G that can be expanded over a very small range, but still it will expand from 2G to 3 inside this turbine, and that work H minus H is enough to generate power over here. And you take that steam, and the question is, why do we have to cool it rather than just dump it into the ocean? Like, why do we have to build a condenser and use the ocean cold water from deep inside to turn this into liquid? Well, the reason is we cannot dump it as it is right now. Why? Because it is at low pressure. You know, when we expand it from 2G to 3, that 3 is really under vacuum. That condenser is under vacuum right now. And so in order to dump it in the ocean, so in the book they just send a pipe like this and say we are sending it into the ocean. No, you can't. You have to put a pump, right? Because if you look what is the saturated pressure of that condenser when the temperature is 15 degrees C, you will find that it's like 0.0 something bar. And so you need to send it to the ocean at 1 bar. So you need a pump. Okay, you need a pump. And in order for the pump to work, the pump needs liquid. And in order for that vapor to become liquid, in order for that 3 to become 4 and it's liquid and can be pumped up to the atmospheric pressure, you need cold water from the ocean to condense it, right? So the reason why we don't throw it away is that it's vapor under vacuum, and you shouldn't also think, well, why don't we just use a compressor to pump it up? Well, the compressor that will pump this guy up to atmospheric pressure will probably use more than the turbine work that you got from 2G to 3, right? So we need to condense into liquid, and then the pump work is so cheap. And that's why when he calculate the efficiency of the system, when he calculate the efficiency of the system, and it should be work net, that work net, he just think of it as work turbine. He neglect that pump. Why? Because the pump work is very small. So he neglect his pump, and he neglect also this pump. What is that pump? This pump is for circulating the ocean water. So he neglect that, and he's right about neglecting this pump, because this is just like pipe loss. It's the water going to the pipe, and you are just calculating its pipe loss. Remember from fluid mechanics, the pipe loss is FL over D, V square over 2G, and we get the F from Moody chart, knowing the Reynolds number and epsilon over D. So he neglect the pumping work over here, and or circulating cold water, and he also neglect this pump. We doesn't even draw it, but it has to be there, and that is the reason why we have a condenser, right? Let alone the vacuum pump that created the flashing effect over here. So this was called the open. Why? Because the seawater come into our cycle, and we basically use it in cycle. And here's the TS diagram for it, right? This is the condenser part, and whether the condenser is closed condenser, meaning that the steam go into a pipe and the ocean water go in different pipe. So this is like shell and tube heat exchanger. Or whether he's an open condenser, condenser where he just spray the seawater in the steam coming from the turbine, and they condense. The steam condense on the water droplet, and at the end of or at the bottom, you just basically get condensed saturated steam. So whether it's that design or this design, the calculation for the energy transfer is the same, and that is the m dot vapor time H3 minus H4, this is how much he lost, will be acquired by the cold water. The cold water. The m dot cold water is coming with H5, and will leave as H4 over here. Alright? So it's basic first law of thermodynamics. Whatever this guy lose, this guy will gain. Okay? And hopefully you read this at home, and this show you step by step how you can calculate the work of the turbine, and how much m dot water, m dot warm is required, and how much m dot cold water is required in the condenser. So m dot cold water is required in the condenser, and m dot warm water is required for flashing at x2, generating m dot turbine. Right? This is the vapor going to the turbine. Very good. And the solution in the book over here. And we talked about how the thermal efficiency of the cycle is work over Q added, and this is when I told you last time that it should be H2G, right? Very good. So here is a sketch of how does the flashing chamber look like. So here is the warm ocean coming, and he is basically trying to reduce its pressure through this design, eventually basically with a drop in the elevation. So as the pressure drop, you will end up separating it into liquid that go back into the ocean again with a pump. Why with a pump? Because the pressure is lower than the atmosphere, so you need to pump it to the ocean. That's why I'm drawing a pump over here. And the vapor go into the turbine that basically expanded, and then it's being cooled and condensed into liquid by the cold water in the ocean, and again that saturated liquid is at lower pressure. That's why you need another pump to take it up to atmospheric pressure and throw it in the ocean, right? So pump to extract this, a bigger pump to extract this, and this pump is basically to circulate the cold water, right? Very good. This is a closed system, and we said in the closed system the heat exchanger, which is a boiler, and the heat exchanger, which is a condenser, just heat and cool the working fluid, and that working fluid can be anything, right? And we saw the paper over here that basically was discussing the advantage of using exotic fluids as the working fluid that goes through the turbine, condenser, boiler, and so on, and the pump, of course, right? So now I want to talk a little bit about heat transfer, because in the book, in the examples, they would ask you to calculate the area of the condenser and the area of the boiler, or basically the evaporator, the place where, especially in the context of a closed system. So in a closed system like this, you have got two heat exchangers, okay, and you will tell you how much is the area, because it's a big deal. That area is going to be really big. Okay, why it's going to be really big? Because the delta T is very small. Remember, we were hoping the maximum we can get was like 27 degrees C or something, and so if you will have big delta T over the heat exchanger, the boiler, and the other heat exchanger, which is a condenser, then what is left for the steam turbine to work on? Nothing, right? So you want to make this delta T as small as possible, and this delta T between the cold water and the vapor as small as possible. So with delta T as small as possible, from heat transfer, from the heat transfer course, you will realize that, well, I actually have a very big area, right? Because what's the equation of the heat transfer? Q dot is UA delta T, right? U over all heat transfer coefficient multiplied by area multiplied by delta T. And by the way, I have all my heat transfer lectures on YouTube too, so you can go through them, especially the chapter about the heat exchanger if you don't remember it. But a summary of that heat transfer chapter on heat exchanger is the following. So any heat exchanger, including our boiler in this scenario, in this chapter, is basically a place where hot fluid and cold fluid find themselves next to each other, separated by a wall, the pipe that's separating them. Alright? And your job is to calculate that area. So the what is the area? The area that get multiplied by the overall heat transfer coefficient, and this is a reminder what is the meaning of that heat transfer, overall heat transfer coefficient. It's basically the addition of all the resistance that the heat transfer had to go through. So there is an internal heat transfer by convection, by convection, external heat transfer by convection outside the pipe, and the pipe thermal resistance itself. Okay, and so 1 over UA is 1 over HAI plus R conduction plus 1 over H out A out. So this guy represents those three guys together. And at the end of the day, the Q, the heat transfer going from the hot to the cold, is UA delta T. So, okay, good. So if he asks me what is the area of that heat exchanger, and hopefully he will give me the U, because otherwise we need to do this, and that's again from the heat transfer course. So the heat transfer course was all about calculating that H and that R and that H, and then you will be able to calculate that U. And again, if you go to the YouTube, you'll find all the heat transfer lecture over there. But in this course, don't worry, I will give you the U. So as far as this course is concerned, you will be given the overall heat transfer coefficient. And so you would know this equation. Q is UA delta T. He's asking for the area. We better get the Q and the delta T so that we can calculate the area, given the overall heat transfer coefficient. so the Q dot, how we can calculate the Q dot? Well, the Q dot is from thermo. The Q dot is that this guy need to take into the ocean, back into the ocean, is the m dot steam multiplied by H minus H, right? That is basically this. The Q that the steam need to lose is m dot steam, which is going through the turbine, time H3 minus H4. He come to us as H3 and he need to leave as H4. So this is the Q dot which the ocean water need to take away from us so that we can become liquid and we are ready for the pump that will pump us up to the atmospheric pressure. Good, we got our Q dot then. So now the delta T. You think it's easy, but it's not. So what is the delta T? Well, that's the difference between the hot and the cold. And here is the problem. So the hot is steam, right? Condensing steam. He comes as H3, he's leaving as H4. All this thing happen at one temperature, 15 degrees C, for example. But the ocean water that's coming at ideally, you know, we said what, maximum 4 or something. But the point is he will come at a small temperature and he would leave at a higher temperature. And therefore the delta T between the steam and between the cold water is different during the pass of the flow. So as the water is going cold in, cold out, the difference may be big at the beginning and get smaller and smaller. And so you are wondering like which delta T I should use. And it's not let's add this plus this and divide over 2 and use mathematical average. So mathematical average work if the difference is not really that big. The difference between here and here is not that big, which actually could be the case in many scenarios. But what is the most accurate way? Logarithmic mean temperature difference. Okay, and this may look a little bit scary, but it's not. It's actually a very easy concept. The concept is basically saying that if you have big delta T or different delta T at the inlet and the outlet, what is really fair is to use this, the logarithmic mean temperature difference. It's the delta T at the beginning minus the delta T at the end divided by ln delta T2 over delta T1. Okay, so delta T2 minus delta T1 over ln delta T2 minus delta T1. And what's delta T is the inlet and out, the inlet and the outlet over here, and the outlet and the inlet over here. So the question would be, so which one is delta T1? Is it the right one or the left one? And who's right and who's left? It doesn't really matter. Why doesn't really matter? Because You just take this as delta T1, this become delta T2, and you realize that whether you're gonna say delta T1 minus delta T2 divided by ln delta T1 over delta T2, or the opposite, like this, delta T2 minus delta T1 over ln delta T2 over delta T1, it would be the same. Why? Because ln 1 over x is minus ln x. So either way, you will end up with a positive number over here. So the end of this calculation will end up basically telling you, well, it's not really 10, it's not 20, it is like 16. Why? Because you did this. You said 10 minus 16 divided by ln 10 over 16. Right? No, we said what? 10 and 20. So 10 minus 20 over ln 10 over 20 is the same as 20 minus 10 over ln 20 over 10. Okay? Alright, well, you will see it later. So this was for parallel flow or counter flow. We use this formula. Now for other configuration that is not pure parallel flow or counter flow, like shell and tube, or this is shell and tube but two shells. So the flow of the steam is moving in that shell and is leaving here going to the second shell, while the tubes basically are going in their path like this. And then they will call this one pass, they will call this two pass. Actually, this is two pass and this is four pass of the tubes. Or close flow. For all those different configuration of heat exchanger that is not parallel or counter, one should use the logarithmic mean temperature difference, like what we said before, but with the addition of a correction factor. What is that correction factor? He's basically saying you don't have counter flow or parallel flow. You have all those weird shape, and those weird shape will put a penalty on the delta T. You think you have this much delta T, but you actually don't, because I mean, look over here. T1 is meeting T2, but also meeting T1. So you think you have this big delta T between T1 and capital T1 and small T1, where T1, capital T is the shell and the small t is the tube. But that guy is actually also meeting this guy, which is smaller temperature difference. Right? So where do we get that F? So that F will come from charts like this. Right? So in the homework, if you have a problem like this, you can get those charts from the heat transfer web pages. And in the exam, I will make sure that if I give you a problem on this, I will give you this chart. So what does this chart say? It say, well, you want your F, you need your correction factor, the one that you multiply the logarithmic mean temperature difference with. And you are wondering, is it 0.7 or 0.8 or 0.9 or hopefully 1 even? That's like perfect. So what is that correction factor? That correction factor will come from over here, this number. You need to know where you are on the x-axis and which curve you are on. So the x-axis is done for T. Let me shrink this a little bit. T out, small t out minus Ti. T out and Ti. That is the tube side. Divided by capital Ti minus small ti. Capital Ti minus small ti. That is the formula. We follow the formula to use the chart. So if we know which one we are by plugging those temperature difference, you then come over here and those curves are done for T capital Ti minus T out, Ti minus T out divided by T out minus Ti, small T out and small Ti, tube side. So you figure out, well, I am 0.6 over here, 0.6, and this curve is 0.8. Sorry, 8. 0.6 and curve is 8. You come over here and you basically say, well, I am 8. Sorry, 0.8 and 0.6. So you meet over here and you go and read your chart F 0.7, and that is the correction factor. So again, different configuration have different charts, right? And we follow them to come up with, here is the cross flow. This is like your radiator, a radiator in the car is a cross flow, okay, where the air would be going one side and the coolant in the is coming on the other side. And the difference, they look the same, but this one, he say both hot and cold basically are divided or unmixed. They don't mix. And over here, one of them is mixed, this guy's mixed, while this guy is divided into tubes. Okay. So, and the Ti and T out, small Ti and T out, refer to the one that is going through the division or unmixed, and the capital T is the one that's going through basically bulk flow. Okay. So think about a flow going through a bunch of tubes. So the air around the tubes will be the unmixed one, and the one going through the tubes will be, did I say that's right? The one that goes through the tubes will be the unmixed one, while the air going around them will be the mixed one, because he just go as bulk. Now if you partition him with baffles, then both of them will become unmixed. Right? So you got the coolant going into tubes, and you got also the air going through baffles that divide them, that become both of them unmixed. In any scenario, you find the right configuration, you read the R and the P, right? The P is for the x-axis, the R is for the curves. You find out which curve you are on, what's the x-axis value, and you go and read the F. Okay, so now once I have the F, what do we do with it? We then calculate the area required. And so in this example in our book, he said a closed cycle, OTEC, ocean thermal energy conversion, right? So the fluid is doing this, he's running on in his own Rankine cycle, boiler, turbine, heat exchanger, which is a condenser, and then pump, and repeat the cycle. And while he's doing this, he's being boiled by, he's boiled at 22. How come he's boiling at 22? Because that's not steam, that is basically propane, I think, propane, right? So you can boil propane, right? That's what we do grilling with in the backyard over here, right? So he would boil at 22, but at what pressure? At, you can see the pressure, so really high pressure. So 22, and it's 8 bar roughly, and he condense at 11 degrees C, become liquid, but at what pressure? 7 bar, 6 bar. 1 bar is 100 kilopascal, right? So really high pressure. So this cycle is going through a really high pressure, and therefore the evaporator and the condenser probably have very thick pipes to take all that pressure, right? Because what is on the other side? Ocean water at atmospheric pressure. And what's on the other side on the condenser? Ocean water, but cold ocean water, again at atmospheric pressure, right? So the pipe need to take 7 bar difference between the high pressure propane inside and the atmospheric ocean water on the outside. Alright, so he said this power plant basically is going to generate 125 megawatt. Where is this 125 megawatt coming from? M dot time this H1 minus H2 inside the turbine. That's how he's gonna go the 125 megawatt. How the pump work? Yes, of course you have to subtract pump work, but you will see in a lot of example he will neglect that pump, and he will even neglect the pump circulating the cold water and the pump circulating the warm water too, because he would think those are nothing basically compared to the turbine work over here. But of course an accurate calculation would require that M dot, and require this M dot, and require this M dot. Okay, so very good. So 22 propane, 11 degree propane, and the seawater is coming at 28, very hot, right? And leaving at 25, and the cold water coming at 5 degree and leaving at 8. Okay, so determine the propane flow rate. I will probably get the propane flow rate from saying that the 125 megawatt is going to be M dot times this delta H. So once I get those two H's, H1 and H2, I will be able to calculate the M dot steam, M dot propane, and the evaporator and condenser surface area. That's why I was telling you we need the heat transfer equation, the equation that say that Q dot from thermo, that Q dot, which is m dot propane time H2 minus H3, that m dot is the same as the m dot is the same as the Q that's basically absorbed by the cold water. So that Q is going to be UA delta T. U over O heat transfer coefficient, the area of the heat exchanger over here between those two guys, the heat exchanger, and the delta T between them, right? And he want to do it for the hot and the cold as well. Very good. So the two H's, how we can get H1 here? That is easy. That's saturated vapor at 22. So you come here at 22 and you tell yourself which H I should get. HG. That is H1. Right? The 918, that's H1. Very good. Now how about H2? How can I get H2? Well, isentropic expansion first. We get 2S. How do we get 2S? Same entropy. S1 equal S2S. So you got yourself the H1 and you also got yourself S1. This is S1. The 5.621, that is S1. You would say S2S is the same as S1, and once you got S2S, what do you do with it? You got the entropy over here. You can get X2S, right? Once you have the entropy over here, you can get the X, the quality from that S minus this S divided by SFG. What is SFG? The S of the saturated vapor minus the S of the saturated liquid. How do I get this? From 11 degree, I come here and I got myself SF and SG. He even super nice, he gave us SFG directly. So this is guy, okay? So once you get the quality over here, we calculate the, once we get this quality, we can calculate the H over here, right? H2S. Why? Because it's going to be H3 plus X2S time HFG. And you got yourself, here is the HF and here is HG, and again he's super nice, he subtract them and give us the HFG. So you got yourself H2S and H1. You are ready now to calculate the isentropic work, H1 minus H2S. But if you want to get the H1 minus H2, he will tell you what's the turbine efficiency, 0.9. And so we know that the the work actual divided by work ideal, H1 minus H2 divided by H1 minus H2S is the 0.9. And that's how you will be able to calculate H2. Alright? So, and by the way, he gave us the U. Again, in this course, you will be given the overall heat transfer coefficient. But in heat transfer course, you can calculate this U from all the different H's across the heat exchangers. Right? So this is what we just explained. How he's calculating the S, and from that he will calculate the quality, and from that he's calculating the H to S, and from that he calculate work ideal, and then work actual, and from work actual he calculating the H2. Very good. And finally the equation to calculate m dot propane, H1 minus H2, work actual multiplied by m dot is the power. Of course, in this calculation, he assuming the electric generator is 100%. In the exam, if I give you what is generator efficiency, you just add it to here, right? You would say m dot propane time work actual time eta. Eta generator would be the power. Now for the area, how we calculate the area. So let's start with the boiler side, the evaporator basically. And so he's saying, let me calculate the Q dot that the guy require. So the Q dot will be m dot, and he come at 4 and he leave at 1. So m dot, and here is basically the two H's. Now there's something weird over here. Look at this and tell me what's wrong. What is wrong is basically saying that H inlet to the boiler is H, what is that? H3. So he's neglecting the pump. He's saying, well, the pump work is nothing, I'm not gonna even calculate it. So, and he's right a little bit, because again the pump work is very small. Okay, but that is approximation. Again, a more accurate calculation would say, no, let's go and calculate the pump work, and from that calculate H4, right? But anyway, we understand his approximation, and in the exam you should do the same thing too. You would say, but you would write before this, you would say neglect pump work, then Q evaporator will be m dot H1 minus, not H4, H1 minus H3 even, which what he did over here. Okay, so he got himself the Q that the evaporator need. Now the question is, how much is m dot and how much is the area, right? So sometimes he asks about the area, and sometimes he asks about the m dot. In this case, he asked for all of them. He said calculate the surface area and the m dot water, m dot warm water and m dot cold water as well. So to figure out how much m dot warm water and how much area, we need the heat transfer part, right? And so here's how much Q we need to get out, and he's saying, well, let's use the logarithmic mean temperature difference. Why? Because I mean, he's come at 28, he leave at 25, and that warm water, the propane is coming here at 11, neglecting the pump work, rise up, and then stay at 22. So what is delta T that we should use? You will see a little bit of weird approximation over here, right? And so here is the logarithmic mean temperature difference calculation. So the 28 leaving at 25, that's understood. 28 and 25, right? What is not understood is, or weird, is this. You see the propane coming at 11, rising up, and then boiling at 22. So that 11 is nowhere to be seen over here in that place. And why is that? He neglected that part. He basically said that I just have propane boiling at 22. Well, does he has the right to do this? Well, this is called sensible heating, and this is phase transformation, right? So this takes a lot of energy to boil. The sensible heating is very small. It's m dot Cp delta T. So one reason for neglecting this part, yes, m dot, that part Q is small, but also when you think about it, he's erring on the safe side. So if he have said I have 11 degree, he would think, wow, look at my big delta T. I don't really need that area, that much area. I can work with a smaller heat exchanger. But in fact, this finished very quickly. And for the majority of the time, the propane will be boiling at 22 with smaller delta T between him and between the warm water. So by neglecting this part, you are gonna come up with a bigger area for the heat exchanger. So you are making it a little bit safer, right? So later on, when he get the area, the surface area, or the heat exchanger get a little bit fouling because of all the dirty seawater coming through it, you will have extra area in your design to play with, right? So now, so the problem is a little bit simplified. So now we just have 22 propane being heated by 28 water at the inlet and 25 water at the exit. So is delta T1 and this is delta T2? Yes. Does it make any difference? No, it doesn't. You can think of them as 28 minus 25. Like you can think of this delta T1 and this delta T2, or this is delta T2 and this is delta T1, right? But let's come up with plus minus, the bigger number minus smaller number, easier for our calculation. But again, doesn't make a difference. So 28 minus 22, that's delta T1, minus, what's delta T2? 25 minus 22. Ln delta T1 over delta T2, the same thing. So it's 6 minus 3 over length 6 over 3. And what I was saying all in the previous slide was that 6 minus 3 divided by length 6 over 3 is the same as 3 minus 6 divided by length 3 over 6. Anyway, so the difference is not 6 degree and it's not 3 degree. The difference turned out to be 4.3. Okay, and when you think about this is, so if we have used the mathematical average, what will happen? Mathematical average will have said you got 6 over here, you got 3 over there, add them, that's 9, divide over 2, 4.5, right? So the 4.5 will be the mathematical average, 4.3 is the logarithmic mean temperature difference method calculation, which is more accurate. Alright? So now this is assuming a counter flow. So this is assuming basically one of them is going this way while the other one is basically going the other way, right? So a pure counter flow would be this calculation. If it's any other design, you will have to visit those charts and get yourself, if you set shell and tube or something, and get yourself a correction factor to multiply it by the 4.3, and he will make it a little bit smaller, right? You multiply the 4.3 by 0.7 or something, it will be smaller. So we got ourselves the 4.3, and here is the heat transfer equation. Q is UA logarithmic mean temperature difference, right? We got this, we got this, we got this, we calculate the area. And he will do the same thing over here. You can see it. Now for the m dot, how much m dot water is needed? That is simply the first law of thermodynamics. That's simply how much Q you need. I got it from the propane. Well, that Q dot is m dot water CB delta T, right? Or m dot water multiplied by delta H. So the Q that the evaporator required is m dot delta H between this place and that place. Alright? And you better get that H so I just noticed that he's thinking that it should be the propane. That is not correct. So the m dot warm water is that H minus this H at 28 and H at 25, right? Not the H of the propane at 22 and the H of the propane at 11. That is, this delta H is not correct, right? So this is wrong. Now for the cold side, you will see how same thing. He needs to calculate his logarithmic temperature difference between propane that's sitting at 11 and the cold water that's coming at 5 and leaving at 8. So here is the 11 minus 5 and the 11 minus 8. Okay, so 6 minus 3 divided by length 6 over 3, same thing, 4.3. And the heat transfer equation Q is UA delta T. Delta T is done this way, and from that he calculates the area. Alright, and in order to calculate the m dot cold water, you would say how much Q dot condenser need, and you need to multiply the m dot cold water times the H of the cold water at 5 and the H of the cold water at 8. He did it here correctly, right? And from that you'll be able to calculate the m dot cold water. Very good. So the thermal efficiency, again, power output over the Q input, and you see how it's like 3%, and we understand why, because of the small delta T. So you don't really have that big efficiency to start with, and that is nothing to frown about, right? I mean, it's said that it's small, but the what will make this work or not is what is the price of the kilowatt hour, not the fact that it's 3%. right? So I mean, we are not shocked that it's 3% because we are not giving him enough delta T to actually run a decent Rankine cycle. So, so this is one concern, right? The small delta T. So the small delta T result in small efficiency, and as a result, to get a decent power output, that we claim we really have a power plant, we need to have a huge Q dot, right? So that this huge Q dot get multiplied by 3%, and you still get something decent to be able to sell to the community next door. So to get a huge Q dot, what is the problem? And I mean, the ocean is filled with hot water. Well, that require huge heat exchanger. That's why we did all those calculations on the heat transfer side. So you need all this area. We need 600,000 meters square in that example that we had. It's a huge area for the heat exchanger. So you can imagine how big this heat exchanger is. And actually, the design for those big power, for those ocean thermal energy conversion system, was they would imagine them, they are the size of an oil rig, like the one that with a helicopter can land on. That's how you can build it, so that it can generate enough power. So how we can reduce that surface area, or basically how we can make it cheaper. I mean, if we are not going to reduce it and you are stuck with that big surface area, so at least can we make the heat exchanger, because both of them are heat exchanger, the condenser and the boiler, can we make it a little bit smaller? Can we make it compact? Because otherwise it will be this big. So you can imagine a big floating power plant, and this is where the helicopter would land, and you say, well, this is the ammonia tank because it's running ammonia, but the point is that the warm water coming from the ocean surface is coming here, and the deep cold water is coming from deep inside, and this thing would be really huge. Okay, so here's another design, basically, or the way that he will extend the pipe all the way. So a telescopic pipe that will take him all the way down, so that he can harvest the cold water for his condenser. Okay, so how we can make the heat exchanger smaller, because they have those compact heat exchanger that you see them in the air conditioning industry, those like they basically plate condensers and plate heat exchangers, right? They are very compact, but those usually are very thin plated, and so they will not sustain, how much did we say, 9 bar on one side and 7 bar on the other side. The heat exchanger of the boiler would require 9 bar and the condenser requires 7 bar. So how can we make the heat exchanger very thin, like a plate heat exchanger, and still be able to sustain that big difference between the propane boiling at 9 bar and between the seawater that is sitting at 1 atmosphere? So let's think about this a little bit, how we can do this. So the propane, we have no control over. His TS diagram tell you, if you want to boil at 22 degree C, you have to have 9 bar. There is no question about it. And if you want me to condense at 11 degree C, you need to make me do this at 7 bar. That is just the thermodynamic of propane. Okay, and switching to other fluids, I mean, we'll change a little bit this, but not much. That's not the solution, from ammonia to propane to all those things. So what is this, how we can do this then? Well, maybe the other side, the water, can be also at 9 bar. If the hot water is at 9 bar, then the heat exchanger can be very thin. And so you are probably thinking, well, let's then pump the water to 9 bar because the pumping power is cheap, right? But there is even a better solution than this, than pumping the water up. Okay, and so in order to use those very compact, very thin heat exchanger, they decided, someone came up with this idea. He said, if this is the surface of the ocean and this is where the hot water is coming, and you see there's a buoy here that's basically holding the pipe in place. Now he said, why do we have to put the boiler or the evaporator over here? Why don't we take the hot water in an insulated duct run by a circulating pump that is very cheap to pump? So this pump is not pumping the water to 9 bar. Okay, no, this pump is just to overcome the friction in the pipe, which is small, especially if the pipe is really big. But by sending the hot water to this height, 100 meter down, the hydrostatic pressure of the water, I mean, shut down the pump, don't even run it, and tell me what's the pressure over here. Well, the pressure here will be 10 bar. Because why? Because I am 100 meter deep without any pump running, but the water will just be sitting in the pipe, sitting here at 10 bar, sitting here at 1 bar. Okay, so the reason why it got higher is because the hydrostatic pressure. And so now if I turn this pump, it will overcome the friction and it will start circulating the pipe. Now the propane or the ammonia or whatever the working fluid, he will be coming on the pipes, running by his own pump, right? As he's going here, and he will go through the heat exchanger. Now 9 bar on one side, 9 bar on the other side, more or less, and you will basically have a very compact heat exchanger that you can bag the 600,000 meter in a very tiny space. And the same thing for the cold water. So the cold water coming from here will get pumped up to the height where you got basically the evaporator. So you get the 9.9 bar in the evaporator and you get 5.4 bar for the condenser, and you will end up having very small delta B across the heat exchanger, which will allow you to come up with very thin and compact heat exchanger. So needless to say, all those ideas are on paper. Why? Because, well, they try to build a bunch of ocean thermal energy conversion system in Africa and in west of Africa, but it's just how corrosive the environment is and the economy of those things. It does not really make it very effective unless it's really big, and that require huge investment to build something like this, and demand for it too, right? But for now, this is the technology that they designed for.